Let's take a look at the dot convention as it applies to magnetically coupled coils. If we have these two magnetically coupled coils, we have current I1 flowing into this dotted terminal. That means there's going to be a voltage sensed at this magnetically coupled coil at the dotted terminal at that coil. So this current flowing into L1 will produce a magnetically induced voltage V2 across coil L2 with the positive reference at the top where the dot is. In figure B, we still show I1 flowing into the dotted terminal at inductor L1, but the dot at the magnetically coupled coil L2 is at the bottom of the coil. So now the magnetically induced voltage will still have the same V2 magnitude, M di1 dt, but the positive reference will be at the dot. So if we call V2 the positive reference up here at the top, it'll be a negative M di1 dt. So that's what we mean by the dot convention. We know if we have for self-induced voltages, I1 will produce a self-induced voltage, or VL, plus or minus, sorry, that's our plus minus, V1 across L1 according to passive sign convention. And that'll be the same in both of these circuits, A and B. The difference is where the positive reference of V2 will actually be. So we could rewrite this as we have a plus and minus M di1 dt in this direction. Let's say we have current entering the non-dotted terminal. If the currents enter the non-dotted terminal, then the positive reference of the mutually induced voltage will be down here at the non-dotted terminal. So if we consider the positive reference at the top, then that's a negative M di1 dt. If we have the non-dotted terminal of L2 up here at the top, then the reference would be plus or minus. So the positive reference for the mutually induced voltage will be at the dot if the current inducing the voltage I1 is flowing into the dot. It will be not at the dot, at the non-dotted terminal, if the current inducing the voltage is flowing into the non-dotted terminal. Okay, let's look at this example then to help us. So here we want to determine the voltage V1 if I2, 5 sine 45t, is flowing here into the non-dotted terminal of L2. So what we know is that the mutually induced voltage across L1 is going to be down here at the non-dotted terminal. So we'll have the positive here and the negative there, and that will be Vm. So we can say that our Vm is going to be equal to M di2 dt. And so that case is going to be equal to 2 times the derivative of 5 sine 45t. So it'll be 2 times 5 times 45 times our cosine of 45t, because the derivative of the sine is omega times the cosine of omega t. So that's equal to what? That's equal to 450 cosine 45t, and that will be volts. So that's Vm, but V1 is going to be the negative of that. So V1 is equal to, it's not just equal to negative Vm, it's equal to L di1 dt. According to passive sign convention, the positive self-induced voltage will be at the top, but it'll be minus Rm di2 dt, or it'll be equal to, since I1 is equal to 0, it's just going to be equal to 0 minus our Vm that we have up here, or equal to negative 450 cosine of 45t, and again that's in volts. So we do have both the self-induced voltage across L1 plus the mutually induced voltage. In this case, from the positive reference up here at the top, we have our mutually induced voltage has a negative reference. So let's look at another example. Here we have I2. I2 is flowing into L2 at the non-dotted reference, so we want to know what will be the positive reference across L1 due to the mutually induced voltage. Well, again, since it's flowing into the non-dotted terminal, we're going to have a VM in this direction. The self-induced contribution, that'll be up the top. So in general, our we do have an I2 flowing. In general, our V1 is going to be equal to our L1 di1 dt minus that VM, or equal to that's equal to 0, so it's going to be equal to 0 minus is this the same problem? It seems like the same problem. Well, it seems this is the same problem, but that's going to be our, we still have our m di2 dt, so our m is again 2, right? So our m is our 2 Henry times 5 amps times our 45 cosine of 45 t, and that's gonna end up to be equal to negative 450 cosine of 45 t volts. Seems like the same problem as the last one. Here we have a slightly different problem. Here, this slightly different problem is we have I1 flowing into the dotted terminal. So, and we want to know what V2 is. So now we can determine our V2, and we'll do it the same way. We'll say, the positive reference here, since I1's flowing into the dotted terminal, we're going to get our VM. Whoops, that's wrong. We're going to get our VM at the dotted terminal. So this is going to be the direction of VM, and we're going to get that V2 is equal to L2 di2 dt. And again, since this reference of V2 and VM are opposite, we're going to get negative M di1 dt. And since that's 0, we end up just equal to negative M, which is the 2 Henry. And then the di1 dt, that's just going to be negative t times negative 8. So we're going to get positive 8 amps times e to the negative t, or negative 16 e to the negative t volts. Okay, so that's a couple of examples of these mutually induced coils and their self-induced and mutually induced voltage across them, where one of the currents was 0, so we only end up with a mutually induced voltage. So a problem you could try now is, you can try this on your own, where you have a current I1 as given, and we have L2 is open circuited, so find V2. So if L2 is open circuited, what does that tell us about the current I2? Make sure you understand that, and then you can determine V2 in these two different scenarios. The difference between the two scenarios is where the dot is. The dot is the same on L1, but the dot is at the top of L2 in A, the bottom of L2 in B. So give that a try.